Hey guys, today's video is going to focus on some basics of the model of the atom, and then we're going to get into a discussion concerning things like atomic mass units, mass number, atomic mass, and how we kind of come up with the atomic masses that we're familiar with on the periodic table, taking into account things like isotopic abundance. Okay? All right, so first things first, let's start with just the basics of the atom. Now again, we kind of got into a discussion on this on Thursday and Friday of last week, but what I really just want to showcase is where we're going to start, and then eventually, obviously our models in class will become more sophisticated and complex. So let's say, for instance, that we have the following kind of representation of the nucleus. Okay, what I've done here is I have 7 kind of subatomic particles, 3 of which have a positive sign in the middle, 4 of which do not. Okay, this is again going to represent our nucleus, where this kind of open circle here that has nothing in it is going to be a neutron. This one that has the positive sign in it is going to be our proton. Surrounding our nucleus are going to be what we call energy levels. Okay, where our electrons reside. So there's going to be an electron, we have maybe another electron kind of floating over here. Now again, this first kind of circle denotes that that is the first energy level. This would represent our second energy level here, okay? And so let's say this is again just a very straightforward model of the atom. So again, that's the electron. We've already kind of dubbed this the nucleus. And then here we have our energy levels, okay? So I guess the first question might be, what element is this, right? We know this has to be lithium because we have 3 protons, okay? The number of protons, or what we call the atomic number, is what dictates what an atom actually is, right? What element it is, okay? So this is a great way to depict this atom. Alternatively, we could use the following notation. We could say something like 7/3 Li, or perhaps just writing lithium 7. And so what this notation means, this bottom 3 here, again, is one of 2 things. Either it's the number of protons, or, and again, these terms are synonymous, it's the atomic number. Okay, so that bottom number is always the number of protons, the atomic number. Again, that's what dictates the identity of an atom, or of an element. This top number here, this is going to be our mass number. And this is merely the sum of the number of protons plus the number of neutrons, okay? So that's the sum of the number of protons and the number of neutrons. So if we wanted to do some quick math, right, if we know that 7 is the sum of protons and neutrons, and 3 is the number of protons, well, 7 minus 3 gives us that we have 4 neutrons, okay? So again, by taking the mass number and subtracting from it the number of protons, we can arrive at the number of neutrons. Now again, this kind of model of the atom is kind of classically called the Bohr model. It's really good in a lot of different ways. It also has a number of limitations. As we get into our second unit concerning really just kind of the electron, we will get into a little bit more detail about how those things are organized, okay? So let's just do some quick record keeping exercises. Let's say we're given, I apologize about that. Let's take a look at this second way to notate lithium, kind of 7/3 here. If we just say lithium 7, what we'd have to do is we'd have to take out a periodic table and we'd actually have to look up what the atomic number is, right? So I take out kind of my handy dandy periodic table. I'd identify where lithium is, and I'd say, oh, the atomic number or the number of protons is 3. Okay, so this notation's nice because it already gives you the atomic number. You don't have to look that up. This one, maybe you got to crack open that periodic table. Okay, so let's take a look at the following examples. Let's say we have 25/12 Mg. Let's say we have 40/20 Ca, or calcium. And things will kind of ramp up a little bit, but I don't know that we'll have a whole lot of difficulty here. All right, so what I want to do in all 3 circumstances is really just, like I said, do a little bit of record keeping. I want to come up with the number of protons, neutrons, and electrons for these 4 examples. So straight away, as far as the number of protons goes, that's that bottom number right, in all four circumstances. That is your atomic number. So again, magnesium is only magnesium because it has 12 protons. If it had a different number of protons, it would no longer be magnesium. So we're looking at 20, 9, and 13. Concerning the number of neutrons, it's simply subtraction, right? So 25 minus 12 is 13. 40 minus 20 is, well, 20. 19 minus 9 is 10. 27 minus 13 is 14, okay? Now, number of electrons, for these, we're gonna kind of chunk this out a little bit. For these first two examples, we have neutral atoms, right? So the number of protons will be equal to the number of electrons. If protons are positive and electrons are negative, that is to say that if there's no charge, they'll cancel each other out perfectly, okay? So 12 electrons for our magnesium atom here, and 20 electrons for our calcium atom there. So again, protons equals electrons for neutral atoms. Now, these are not atoms per se, right? These are ions. These are carrying charges. And so for this one, this is no longer a fluorine atom. Rather, we call this the fluoride ion, and it carries a 1- charge. That means that there is an abundance of negative charge, namely that there's one more electron than there are protons. So if we've already identified there are 9 protons, that is to say there must be 10 electrons. Again, not an aluminum atom, rather this is an aluminum ion. Now in this case, we actually have an abundance of positive charge, which is to say that we have more positive charge than we do negative charge. So if we've already identified that there are 13 protons, there must be 3 less electrons. And so we arrive at 10 electrons for that ion of aluminum, okay? So if we investigate said magnesium on the periodic table, okay, I think what you'd find is, again, and I can actually pull this out, and when we take a look at magnesium on the periodic table, we see this number here, 24.30, and that's the atomic mass, okay? So let's kind of go back to that example. Let's actually, I guess, write a question. We're gonna say, why is Mg, or magnesium, 24.30 AMU, which stands for atomic mass units, on the periodic table, right? That's really kind of peculiar, right? That we would have kind of like this decimal, because normally, masses are largely just the sum of protons and neutrons. Electrons are so light relative to protons and neutrons, they really have no bearing on that, okay? So we want to start to differentiate a little bit between the terms atomic mass and mass number. So we're going to say that our 24.30, again, AMU, those are the units, is the atomic mass, not the mass number. Okay, so these things are a little bit different. And the idea here, so if we're just going to kind of quickly define these, we'll say that the atomic, there's a weird way to spell atomic, atomic mass is the weighted average of all different types of an atom. Okay, so the atomic mass is the weighted average of all different types of an atom. We're going to see what that means here in a moment. Okay, and we're going to say that so again, if this is one definition, we're going to say that the mass number refers to, again, the sum of the number of protons and the number of neutrons for a type of that atom. And so this kind of brings us to the concept of isotopes. And again, this may be a term that is familiar from previous science classes. When we talk about isotopes, the idea here is that these things are atoms of the same element, but with different numbers of neutrons. So, an investigation of magnesium, right? Let's say we have 3 different kind of dominant types of magnesium that exist in nature. Let's say we have magnesium 24. Let's say we have magnesium 25. And let's say we have magnesium 26. Now again, the idea here is that they're all magnesium because they all have 12 protons, okay? However, they all have different mass numbers. Now, the reason they have different mass numbers is because all of these all have different numbers of neutrons, right? In this case, we have 12 neutrons. Over here, we have 13 neutrons, and over here, we have 14 neutrons. So again, while they are all magnesium atoms, they are isotopes of each other. Exact same element, right? They differ in the number of neutrons and therefore the mass number. So in nature, we would find, or maybe we would look this up, that magnesium 24 makes up 79% of all the magnesium that's out there, right? And magnesium 25 makes up about 10%, and magnesium 26 makes up about 11%. So the idea is that when we reference the periodic table and we're finding that, the atomic mass is 24.30 AMU, the idea is that this is not just an average, this is a weighted average, right? If we were to take just an average between 24, 25, and 26, we'd find that, the average, magnesium atom that's out there weighs, or has a, atomic mass of 25. It's not going to be 25 because in nature we find there's actually a lot more 24 than either 25 or 26. And so the average is skewed towards the one that kind of dominates, right? That has the largest, what we call isotopic abundance, okay? I think this concept will get firmed up a little bit more as we kind of dive into 2 different examples. Okay, so at this point, you can continue to take notes in your composition book, or should you want to, feel free to print out that resource that actually has 2 different questions. And we're going to walk through these questions just to kind of firm up the idea of mass number, isotopic abundance, weighted averages, and how we kind of work through this math a little bit. Okay, so imagine that you've come to planet X, where you know that carbon is abundant, but the isotopes are present in different ratios than here on Earth. So we're told that carbon-12 makes up 65%. Okay, that is its isotopic abundance. We'll label that in a moment. Carbon-13 makes up 30%, and carbon-14 makes up 5%. And we're being asked to solve for the atomic mass. So again, that atomic mass is what we call a weighted average. Okay, so whenever we talk about weighted averages, and as we set up these kind of isotope type problems, the way this is going to work is we're always going to take our mass number for a specific isotope. Okay, so in this case, let's start with carbon-12, and we're going to multiply by its specific isotopic abundance converted to a decimal, right? So whenever we want to take a percentage and convert to a decimal, we merely divide by 100. So we divide by 100 to get the 0.65, and we'll multiply the mass number by, again, that specific isotope's abundance, and we call this the isotopic abundance. Then what we'll do is, in order to figure out the overall weighted average, obviously we have to take care of all of our isotopes. So we'll add that to carbon-13 multiplied by the decimal form of its isotopic abundance, plus 14 multiplied by the decimal form of its isotopic abundance, okay? When we take the product of all these and we sum everything together, we get 12.4 AMU. So again, the atomic mass that we've solved for is 12.4 AMU. And I think kind of a quick check here is that mass numbers are always going to be whole numbers, right? Mass numbers, again, are always just the sum of protons and neutrons. So they're going to be whole numbers. Again, mass number. However, your atomic masses are always, or maybe not always, but pretty much always going to be decimals because they are weighted averages, right? They involve calculations, products, sums. And so very likely we're not going to have whole numbers, but we are going to have a decimal. Okay, so I think that's a quick way to kind of differentiate between the two and make sure we've attended to those things correctly. Moving on to question 2 here. Nitrogen has an atomic mass of 14.007 AMU. There exist two naturally occurring isotopes, that of nitrogen 14 and nitrogen 15. Okay, so we'll kind of keep this in mind. There's 14, there's 15. Here's the overall atomic mass. We're trying to actually solve for the percentages of each. So, different strategy, but the same content. So let's write down what we know. Let's say we were to try to set this problem up similarly to the last problem. I would take 14 multiplied by some percentage, right? I don't know what that percentage is for nitrogen 14, so I'll just call that X right now. I'm gonna add to that, nitrogen 15 multiplied by its percentage. Again, I don't know what that is, so that's gonna be Y. And I'll set that equal to the atomic mass, so 14.007. You'll notice in that last problem here, we were actually solving for the atomic mass because we were given percentages. In this problem, we are not given percentages, rather we're given that final value there. Well, the way that I would approach this is that, X plus Y, we know that all percentages sum to 100, right? So this should equal 100. But you have to remember that we've taken those percentages and in using them, we would have converted over to the decimal form. So actually, X plus Y will not equal 100, rather X plus Y will equal 1. I'm just gonna write this right underneath here. Here is your system of equations that you'll have to use in order to solve for both X and Y, right? I have two variables and I have two kind of unknowns. I have two variables, which are our unknowns, but I have two equations, okay? So whether you use elimination or substitution, you wanna look to solve for X and Y. I prefer substitution, so that's what we're gonna roll with. So I'm gonna say X equals 1 minus Y. All I've done is I've rearranged that equation there. I'm now gonna take this X and I'm gonna plug that in for this equation. So I have 14 times by 1 minus Y plus 15Y equals 14.007. From here, I trust that you can distribute, so 14 minus 14y plus 15y equals 14.007. We isolate for y and solve, y equals 0.007, okay? In order to solve for x, I go back to this equation here, where x is equal to 1 minus 0.007, since I just solved for y, and we find that x is equal to 0.993. So, to report isotopic abundances, which is what the question is asking, I do want to convert these to decimals. So recall that X is the isotopic abundance for nitrogen 14. So I'm going to write nitrogen 14 equals 99.3%. Okay, again, I converted the decimal form back to the percentage form. For nitrogen 15, which again, we were defining as Y, its isotopic abundance, I'm going to call this 0.7%. Again, that is the decimal form back to the percentage, okay? Here's your final answer for example problem number 2. Thanks, guys.